Right, so we've got a question from 2018's BMO1, this question 1. A list of 5 two-digit positive integers is written in increasing order on a blackboard. Each of the 5 integers is a multiple of 3, and each digit 0 to 9 appears exactly once on the blackboard. In how many ways can this be done? Note that a two-digit number cannot begin with the digit 0. Right, we've got a lot of information in this question. Let's just start picking key information out. So we're told that this number is a multiple of 3. So the sum of the digits, so let's say we have two-digit number AB. A plus B must be a multiple of 3. This is just the divisibility rule by 3. And each digit 0 to 9 appears exactly once on the blackboard. How many ways can this be done? Right, I think that's the most analysis we can do of the question for now. Let's start. So where should we start? Right. Let's look at what numbers we can possibly form. So imagine we start with 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're starting with these numbers, right? Let's check. So if we had 1 as our first digit, what other possible numbers could we get? So we've got 1. So we know that the sum of the digits must add up to a multiple of 3. So multiples of 3, let's just circle them. 3, 6, 9. So 1 plus something equals 3, which is 2. 1 plus something equals 5 is 6. And which is plus 3 to get our last term. Not last term, last possible 3-digit number beginning with 1. Now 2. Well, 2 plus 1 equals 3, 2 plus 4 equals 6, and 2 plus 7 equals 9. That's fine. Now with 3. Well, the first 3-digit number starting with 3 is 30, then 33, 36, 39, 4. Now we need to add up, we need to get to 3-digit numbers. So we have 4, and the next 3-digit number is 6, so plus 2, 9 plus 5, 12 plus 8. Notice how that this list here is the same as here. So we're expecting 147 to be our next set of last digits. So we've got starting with number 5 now. 5 plus 1 equals 6. 5 plus 4 equals 9. Then 5 plus 4 equals 12, 7. Is that the same as what we expected? Yes. So we can confidently say that 6, 0, 3, 6, 9. Oh, we made a mistake here. In the question, states that each of the 5 integers, each of the 5 two-digit integers use numbers 0 to 9 once. So that means that when we start with a multiple of 3, we can't have another multiple of 3 next to it. That means we can eliminate 3 from this list and 6 from this list. And 7, we expect 2, 5, 8, 8, 1, 4, 7, 9, 0, 3, 6. Now let's group these somehow. So we know that 1, 4, and 7, numbers starting with 1, 4, and 7, 3-digit numbers formed from them end in the same 3 possible digits. And same for 2, 5, and 8. And since we deal with multiple of 3s, let's write them in terms of their classes of residue. So for 3, 6, and 9, 3, 6, and 9 follow 3k plus 0. And the numbers in this class are 0, 3, 6, and 9. 3k plus 1. example, that's numbers starting with 1, 4, and 7. So we've got 2, 5, and 8. Then 3k plus 2, we have got 1, 4, 7. Nice. Okay, this sort of makes it easier to find how many ways we can get a list of 5-digit numbers. So let's look at our first class, 3k plus 0. We've got the numbers 0, 3, 6, and 9. Now notice that we can't, so the numbers that include 3, 6, 9, and 0 can't be can't be paired with a number from another class to get a 3-digit number. Let's see why this doesn't work. Well, 3 plus 3 and 2, 32, not a 3-digit number. What did we say? A 3-digit number is a multiple of 3. So a multiple of 3 plus another number to form a multiple of 3, that other number must be kind of multiple of 3. So let's see how many possibilities we can form from 0, 3, 6, 9. Well, this residue class is quite special, you could say, because it's got a 0 in it, and we know from common sense and what the question states that 2-digit number cannot start with 0. So that forces the 0 to be at the end at all times, meaning we can have 30, 60, or 90. So let's write that out, 30, 60, or 90. Now if we have 30, what are the other numbers we can form? Well, we can form 69 and 96. What about 60? Well, if we have 60, we can form the numbers 39, 93, and then 90. We can form the numbers 36 or 63. So might I bracket this off? So when we've got 30, I don't know why I've written it so spaced out, but that's fine. When we've got 30 as we can see our fixed slot, the only two combinations we can have are 69 and 96. We've got 2 there, 2 there, 2 there, meaning for our residue class of 3k plus 0, we have got 6 possible, you can say, ways to do the question. Now 3k plus 1 and 3k plus 2. Now just look at this part here, 3k plus 1, 3k plus 2. We need to essentially form a multiple of 3. Now if we choose two numbers from the residue class of 3k plus 1, well, hold on a minute, I've written my residue classes wrong. 3k plus 1 should be 147. 3k plus 2 should be 258. That makes a lot more sense now. As I was saying, to form a multiple of 3, we need to, well, if you choose two numbers from the same class, so 3k plus 1, we've chosen two numbers from here, so we have 3k plus 1 plus 3k plus 1, which gives us 6k plus 2. Now 6k plus 2 is not a multiple of 3, so we can't do this. Now let's say if you choose two numbers from the class here, 3k plus 2 plus 3k plus 2, 6k plus 4, and if we mod that, we get 3 we get 1. So that means that number is not divisible by 3. So our last choice is what we can do is add the choose numbers from each class. So if you do one from 3k plus 1, 3k plus 2, add that, you get 6k plus 3. And when you mod 3, to check whether this number is a multiple of 3, you get 0. So now we know that we need to be combining the numbers from each class. Now what's the best way we can do this? Well, let's start with the obvious or smallest number, 1. So if we start off with 1, how many other, let's just write this on the next page. paste. So we're dealing with these two classes. If we start with 1, and we're trying to arrange these 6 digits to form 3 2-digit numbers, so we have 1. Now let's choose 2. So again, that's the first number from each classes. If we form the number 12, how many other numbers can we form? So we're left with the numbers 4, 5, 7, and 8. And the possible pairs we can make are 4, 5, 4, 8, 7, 5, 7, 8. So let's draw this in sort of a tree diagram sort of way. So if you choose 12, you can choose either 45 or we can choose 54. Let's remember not to forget that option. We'll have that option there. Okay, or we could have done 12, instead of choosing 4 and 5, we could have done 4 and 8, or 8 or 4. Yep. Now from 45 we could have chosen 78 or 87. From 54 we could have chosen 50, 54, 78, 87, 48 we could have chose 57 and 75, and the same for 84. So if you look how many combinations we've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 possible combinations, and that's just for the number 12. Now from here, using the same logic as we've done with 12, how many other numbers can we form? Let's just write them out in red. So we can have 1, 2, we can have 21, we can also have 15, we can have 18, we can also have, well, if you have 15, that means we can have 51. If we have 51, that means we can also have 18 and 81. Now these numbers here, well, we've just looked at 1, and I'll show you why we've only looked at numbers with 1. Because I'll show you why. Well, 12. Now how many, if we start with 12, how many arrangements have we got? Like we said, we had 8, and the same would be for 21, same for 15, same for 51, same for 18, same for 81. If you add this up, this gives us 48. Now, just by using the number 1, we've got 18 possible ways. Now, let's choose our next number from 3k plus 1 class, 42. Now, the issue with choosing 42, or selecting I should say, is because when we were dealing with 15 or 18, with that being our fixed number, we already included 42, just that I haven't written it out. That means we do not have to consider this any further. We know that there are 48 ways to form numbers in the class 3k plus 1 and 3 form 2-digit numbers using these two classes. We've considered all the cases. Now we have to merge this with the answer before. So we said that 2 of our 5 digits, they'd form 6 possibilities, and 3 of 5 digits form 48 possibilities. So we can see this sort of as a tree diagram. So if we choose the first of the 6, we have 48 options. 1, 2, we have another 48 options. 3, 48 options. 4, 48 options. Fifth of the 6 is 48 options, and this is the last of the 6, also 48. So we've just got 48 plus itself 6 times, so 48 times 6, and if we evaluate that quickly, that gives us 240 plus 48, 288. So there are 288 ways that we can have 5 two-digit numbers which each have distinct numbers between them. And that's all for this PMO problem. Hope you enjoyed it. See you in the next. Bye.